Hello everyone. So this is the last topic of our class, topic number 11, which has to do with flow rate and capacity analysis. Now I've taken two topics within this topic out. They're no longer there, the theoretical capacity utilization and the capacity multiplier. Now, so basically the topics that we're going to be covering now today is basically the theoretical capacity, the resource pool, and the normal capacity utilization, not the theoretical capacity utilization. So let's start. So if you guys remember when we we touched a little bit on capacity, we said what's very important for us is the effective capacity. And this is what we're going to be studying. The overall capacity is never realized, so we're going to be talking about effective capacity. Now, it's very important, the very important thing that we need to talk about here is resource units and the difference between resource units and resource pools. So here we have an example of a bakery. So if we have three flexible bakers that can perform any baking activity, which is basically they could do mixing, kneading, and forming of the dough. If they could do all three, then we think of them as one resource pool. So one resource pool. Now, if we specialize the bakers, so one baker only does the mixing and one baker only does the kneading and forming the dough, then we end up with three resource pools. Okay, so you could think of this also in supermarkets. If you have the person handling the cash, if that person does cash handling and packing the groceries, then that would be one resource pool. Now, if you have two separate individuals, one handling the cash and one packing the groceries, then we would have two resource pools. Now, in the case of the bakery, even though we have one resource pool, but we still have three resource units within that resource. So we still have three resource units. And here we still have three resource units. So the number of resource units is not affected by whether you have specialization or no specialization. We still have the same number of resource units. So if we have the three bakers all experience in doing all different three activities, there's still three resource units, but they're in one resource pool. While if each one of them is specialized, then we have three different resource pools, but we still have three resource units. So the resource unit doesn't change, the number of resource units don't change, but the number of pools will change. So the resource units are not going to change the number of resource units whether you change the number of resource pools or not. Now, it's very important for us to understand that combining several resources pools into a single resource pool is a very powerful tool. It's called resource pooling, but it's a very powerful tool that can affect process flow measures in a positive way or improve process flow measures. Now we've seen this. We call this also cross training. So we've seen this in COM 225 at least as cross-training. And cross-training meaning is basically you train your employees on more than one task. So the employee could do a multiple task, and this is quite efficient and effective, especially in times when demand is high. One example of that is at a supermarket. When things are really busy and there's long lineup of customers trying to check out, what happens in a supermarket is they usually have people in the back come and work the cash because they're trained. And once this happens, so you have more stations for customers to check out their items, and that would reduce the congestion or reduce the lineups. So it is a very powerful tool, what we call resource pooling and trying to combine a lot of resources in one pool. Now, now let's look at the equation for effective capacity. And now we get to the first thing we need to look at is what's a unit load. Unit load is basically how long it takes to process one unit by a resource unit. A resource unit, you could think of it as an employee, as a laborer, as a specialist. Sometimes it could be a machine. So basically, unit load is how long does it take to process one unit? In the service industry, how long does it take to service one customer? So now effective capacity of different resource pools is always dictated by the slowest resource pool, which is the bottleneck. So the bottleneck will always dictate the effective capacity of the whole system. So also if we have processes that are in series, and let's say this one is the bottleneck process, so this process takes longer than all the other processes, then the whole system is going to be dictated by this process. So the effective capacity of this process is basically the effective capacity of the system. So we have to remember this. Now let's get to the equation, and the equation is this, which is the effective capacity of a resource pool. So we're looking at a resource pool, and which is basically CI, which is the number of units within that resource pool, over TI. And TI here is the unit load. Now, please do not confuse the unit load. Let's use red here. The unit load, don't confuse it with what we've seen from the previous lecture on flow time. So flow time is different than the unit load. Unit load. So they're totally different things. So let's see this example. So we have, this is an residential insurance claim question. So here the flow unit are insurance claims, and the resource unit are basically these agents that are processing the claims. Two agents are available for the process, so the resource pool has two. And now we have two equations that we might be using: the effective capacity for one resource unit, and then the effective capacity of the resource pool. Now the first thing we want to do is calculate TI, which is the unit load. Actually, it's given to us as 12 minutes per claim, so 12 minutes per claim. And the question asks us for the effective capacity of a resource unit. So be careful. Here they're asking us for a resource unit. It's not for the whole resource pool. So for each agent. So it's the effective capacity of each agent. Effective capacity of each agent, which is going to be one. So it's going to be this equation right here. So 1 over 12, which is going to give us 5 claims per hour. Now the effective capacity of the resource pool is just because we know there's 2 agents, so we know that there's 2 agents here. So we just take these 2 agents and we multiply them by what we got in terms of the effective capacity of the resource unit. So we know how much the effective capacity of one resource unit, which happens to be 5 claims per hour, we multiply by 2 and we get 10. Now we could have used the equation also. We could have said effective capacity is equal to CI over TI, which happens to be CI is 2 because we have 2 agents in that resource pool, and TI is 12, so that gives us 1 over 6, but that's claims per minute, and when we convert it in terms of hour, we should get 10 per hour. So 10 is the same thing as 10 claims per hour. Okay. So basically, this is a good question because it's asked us about the effective capacity of one resource unit and the effective capacity of the whole resource pool. So notice there are 2 different things, because one is for the whole resource pool, which includes all the different resource units within that pool, and the other one is simply just the effective capacity of that one resource unit. So let's move on to another example. Here we have insurance physician claims. And we have a process that starts at the mailroom and goes to data entry, claim processors, and claims supervisor. So we start by, so mailroom is first, then the data entry, then processor, and supervisor. Now, very interesting. If it turns out, so the actual capacity of the process will depend on the bottleneck. So whichever process is the bottleneck is going to dictate the effective capacity for the whole process, because the question is asking about the effective capacity of the whole process. So we're going to calculate each effective capacity for each resource pool separately. So we know that, so these are the unit loads, so they're giving us the unit loads, which is minutes per claim, and this is exactly what it should be. It should be time per job, per claim, per product. This is the number of units in the resource pool. These are number of resource units. So resource units. So a very good method is to always to start calculating the effective capacity of the resource unit, one resource unit, which is very simple. Where in this case we have it's 1 over Ti, and Ti in this example is going to be 1. So remember, the effective capacity is equal to 1 over Ti for one resource unit. And then for the pool, we just multiply that by Ci, just like we did in the previous example. So we get 1. So now we move on to the next resource pool, which is the data entry clerk. The Ti is 5. So the effective capacity for the resource unit is 1 over 5.2. And then we multiply it by 0.8 to get the effective capacity of the whole resource pool. Now we do the same thing for the claim processor and supervisor, get 1.5, 2.0. Now the effective capacity of the overall process is basically dictated by the bottleneck, which is this process. The mailroom is the bottleneck. It has the smallest effective capacity. It could process less than any of the other departments. So this will dictate our effective capacity. So the effective capacity is going to be 1 claim per hour, which is basically the bottleneck, because this is the bottleneck. Or you could think of it as the job or the resource pool with the lowest effective capacity. So now, just because we have an effective capacity of some number, it doesn't mean that we're going to be using that effective capacity. So for example, if we have a process and the effective capacity of that process is 20 units per hour, it doesn't mean that the throughput is going to be 20 units per hour, because sometimes the demand is not 20 units. So what happens if the demand is 17 units? So maybe you will work at 17 and you will be short 3 units per hour, simply because the demand doesn't ask you to do 20 units per hour. So for this reason, we have something called utilization. And utilization is going to be basically our throughput R. So this is the R we've learned in the previous 2 lectures, and it's going to be over the effective capacity, which we've just learned how to calculate. So let's look at this example. So again, it's this, we're still doing claims, and they're telling us there's 400 per day. So this is R, because this is an actual demand of how many they need to do. So given a month, they said it was measured to be $400, 400 claims per day, which is, this is R. So we have to basically convert our effective capacity that we calculated in the previous example by multiplying it by 60 times 8, because we have 8 working hours, and that number was in minutes, so we multiply by 60, so we get 480. Now the capacity utilization is just R over the effective capacity, which gives us 0.83%, 83%. So now the question is asking us what is the capacity utilization for each resource pool. So we continue with the same logic of using that equation to get the capacity utilization for all the remaining resource pools. So the calculations we just made, we need to assume some things in order for us to use that equation. And one of the assumptions is that we're handling 1 unit sequentially. So 1 unit at a time. All the resources are available at the same amount of time. We ignore the effect of setup, and that's exactly what we've done in all the questions. There were no mention of setup. We assume all the resources were available, and we're doing things 1 unit at a time. So effect of product mix. Now in real life, companies or departments don't just deal with one product, they deal with multi-products, and this will affect the effective capacity. Now for us, it's only gonna affect the unit load. So we're gonna it's gonna change how we calculate the unit load, but from there on, the process is gonna stay the same. So for example, here we're looking at the same example, New Life Finance. We still have the same resource pools, but now we have physician and hospital claims. So 2 different products, unit load of hospital and physician claims. And now we have these numbers. So we have 2 sets of numbers. So in this case, what we need a ratio. We need a ratio. In these questions, they will give us a ratio of how much is one product compared to the other. Now, suppose the ratio is 60 to 40%. So 60% physician claim and 40% hospital. Now, in the questions you will see, in the examples we will do, or maybe on the final examination, you will be given that ratio. You will know that ratio. Without the ratio, you wouldn't be able to do the question. So we know 60%, so we take 0.6 of 1, and then we take 0.4 of 1.5, because that's what they're telling us. The hospital's 40% and the physician 60%. So it's sort of like a weighing average. So we multiply 0.6 by the unit load for the physician and 0.4 by the unit load of the hospital to get this number. And we do the same thing for the remaining resource pools. And from there on, we follow the same process. So now we basically so we've calculated the effective capacity for each resource pool for that product mix. Again, we're following the same procedure we did for the examples we've done before. Now this slide gives you a better understanding how it's done. This is the unit load. This is for the resource unit. Then we multiply it by 1. So we get an effective capacity of 0.3, while we multiply it by this one by 8, because we have 8 units within that resource pool, and we get 1.48, and so on. Now again, when we want to answer the question, what is the effective capacity of the process as a whole, mailroom still the bottleneck. It is still the bottleneck. It's the smallest effective capacity, which is 0.83, and that's going to be 50 claims per hour. So if you compare the 0.83 claims per minute, you multiply it by 60, it's going to give you 50 claims per hour. So now we're going to talk about theoretical capacity. And just like we talked about theoretical flow time in the previous topic, there's also a theoretical capacity, because capacity is not realized because of a lot of waste. Things like maintenance, resource breakdown, rework and repetition, setup between different products, non-value added activity, and others. So in reality, our unit load is an aggregation of two things: productive time and wasted time. And if the capacity waste, so our wasted time, is large, then we need to do something to eliminate that waste, which makes it very useful to be able to segregate the wasted capacity from the productive capacity or productive time capacity. So if we were to get rid of all the waste, then we would reach theoretical capacity. And the theoretical capacity is based on the theoretical unit load, which is the minimal amount of time required to process a flow unit if all waste, so all the waste here, is eliminated, gone. So the theoretical capacity is basically the reciprocal of theoretical unit load. Just like we've seen before, that the effective capacity is the inverse of the unit load, the theoretical capacity is the inverse of the theoretical unit load. So now we're gonna see how we're gonna calculate the theoretical capacity if we know the ratio of waste. So the theoretical capacity is basically just the effective capacity without any waste. So there is no waste. If we take all the waste, then we get to theoretical capacity. If we take the waste out of any process, then we get to theoretical capacity. And we're going to use a ratio called the CWF, which is the capacity waste factor, which is a percentage ratio of theoretical capacity. Okay, and to move from theoretical capacity, then we're going to use that ratio, 1 minus CWF. So effective capacity over 1 minus CWF. And we could do the same thing for theoretical load unit, where it's equal to the effective load unit times 1 minus CWF. So the capacity waste factor is basically the ratio of how much of the theoretical capacity is waste. And using that ratio, we're going to be able to calculate the theoretical capacity or the effective capacity, given that we know theoretical and the CWF, or we could calculate the theoretical knowing that we have the effective and CWF. So let's look at an example. So we have a surgery room, and on average, the room performs surgery every 30 minutes. So we're getting a load. Here is the unit load. The effective capacity is two cases, so they're giving us the effective capacity. We're looking at 33% CWF. It is estimated that 33% of the operating room is wasted. So CWF is the ratio of how much there is waste, and that's 33%. They're saying that waste is due to cleaning, restocking, changeover of nurses, fixing equipment, etc. Now we want to compute, first of all, we're going to compute the theoretical capacity and then the theoretical unit load. So this is the equation. And we know the unit load, they're giving us the unit load. And the CWF, we already know this right here. Then the theoretical capacity is just applying the equation, really straightforward calculation. We get 3 cases per hour. Now we want to calculate the theoretical unit load. Now again, it's just applying the equation. And this is the equation. Theoretical load is going to be 30 times 1 minus 0.33, we get 20 minutes. Now just remember that the theoretical unit load is going to be lower than the normal unit load, the 30 minutes, because so much of the time is eaten up by waste. So now we're going to be looking at different tools for managing throughput or improving throughput. And one of them is throughput improvement mapping. Then we have increasing resource level, reducing resource capacity waste, and shifting bottlenecks and improvement spiral. And we're going to discuss each one of them separately. So the idea of improvement mapping is we want to look at where the bottleneck is. Is it internal or external? Now, this equation here is always true. This equation right here, throughput is less than effective capacity is less than theoretical capacity is always true. But sometimes we could see that the throughput is much less than effective capacity, and then we should be searching for reasons, or if the effective capacity is much, much less than theoretical capacity. So if throughput, which is right here, is less than capacity, which is right here, so significantly less, then we could say the bottleneck is external. This is the case that you have the effective capacity, but your throughput is not so your employees are not working up to the effective capacity. And the reason for that is maybe demand is lower than expected. So there is no demand. Or maybe the supply coming from your suppliers is not as high as it should be. So you could be ready to produce, but you don't have the supply material, so there is waiting. So by knowing this, if it's less, so by knowing that your throughput is less than your effective capacity, you could right away search for external reasons. So you know that bottleneck is external. So now what happens if your throughput is almost equal to your capacity. Then obviously your bottleneck is not external, it is going to be internal. It's inside your organization. And the only way to increase your throughput is by increasing capacity at that point. And you could do that by hiring more people, changing the product, adding more product. So what happens when your capacity is much, much less than your theoretical capacity? So your effective capacity is much less than theoretical capacity. And remember, the relationship between the two has to do with waste. So you gotta decrease the waste, get rid of the waste. And you could improve the utilization of the resources, look for wherever there is waste and try to eliminate it. So we talked about throughput mapping, and once we do throughput mapping, then we know where the problem is, where it lies. And in the case, let's go back to the case where process capacity, the effective capacity, is equal to the theoretical capacity. In that case, we could increase the workforce, so the number of resource units, so hire more people. We could increase the size of resource units, and this has to do with a bigger equipment, machines, and so on. Increase the time of operations, which means things like overtime, machines running overnight. We could subcontract. Subcontract is another solution where you could get other company organization to help you out. Or you could outsource some of the bottleneck activities. Also, you could speed up the rate at which activities are performed. So this comes with better training, so your employees could do more units per time period. So let's go into details on what we could do to increase capacity. So we've talked about this, eliminating non-value added activity. So identify the non-value added activity, again, from the customer point of view, and try to reduce them or eliminate. Avoid defectives, rework, and repetition, because all that eats up capacity. So if you avoid all that, it's gonna lessen all these things that are eating up capacity. Reduce things like breakdowns, work stoppage, all that stuff is time wasted in terms of capacity. Your maintenance policies should be better so your machines don't fail as often. Reduce setup loss. So every time we do a setup, that takes time, so we want to be quick at setting up operations. By obviously reducing setup time is key here. So move some of the work to non-bottleneck resources. So when we have not bottleneck resources, so moves that work to other resources. So if you have an employee that is really is doing a lot of work, more than the others, and that person is becoming the bottleneck, then move some of his tasks or her tasks to another employee. Now, reduce interference waste, and we're looking at two things here. Starvation, which basically means that resources are available, so people are ready, machines are ready, but the inputs are unavailable. So these are things that you're waiting for material, so waiting for material or parts, and that's starvation. So you need to reduce that, and the best option is to improve your supply chain relationships with your suppliers so things are available on time. Blocking is the raw materials are ready, the parts are ready, and your employees are ready, and machines are ready, but then maybe there's too much inventory in the system that you don't want to make any more products. It could be directives of management. Maybe it has to do with the market. Maybe the market is not behaving as good as you want it to behave. So For all these cases, this is blocking. And obviously for starvation and blocking, for starvation, better supply chain activity management, and also for blocking, better supply chain management in terms of understanding demand and managing your inventory. So in overall bottlenecks are the most important in processes. So if you need to identify bottlenecks. So if you have a process and this happens to be the bottleneck, this is what's slowing the system down, then you have to identify it. That's obviously the most important, one of the most important steps in throughput improvement. And as we said, you want to increase capacity of these bottlenecks, whether they're internal or external. But remember something very interesting that happens. So every time you add more resources to bottlenecks obviously will disappear, but new bottlenecks will arise. So if this process, so let's look at this example. So this process is now the bottleneck. If we add more resources, so resources, what will happen is maybe this one will become now the bottleneck, right? So now we have to add resources here and so on. So there's a spiral effect, and so always there's new bottlenecks being always coming, new ones arising, and new process capacity increases and so on. So the process is gonna keep going like in circle. But every time you identify the bottleneck, new bottlenecks, and you improve the process, you tend to basically, so the improvements are decreasing at a rate. So the first bottleneck you identify, so this is the first one, it's going to give you a lot of improvement. The second one, it will give you improvement, but not as much as the first one. Then the third one is less, and so on. This is what the spiral effect is all about. So this is the last example we'll do on capacity and throughput. Example number 6, I'll leave that for you guys to do. So now we're in this question, we have two different products. So this is a law firm that does both shopping centers and medical complexes project. And these are the time requirements. And we have the two different products, medical and shopping. We have per number of professionals, this is CI, and these are three different resource pools, but we see something different here. We have the available hours for each one of these resource pools. We haven't seen anything like this before. A month includes 20 working days, and the firm has generated 150 orders, 75 of each, so we have 50% ratio of each. So we have 50% shopping and 50% medical. So the product mix is 50%. The unit load mix we're exactly doing the same thing we've done in previous examples. We have to use that ratio, this ratio right here. And so we'll start with paralegals. So we have 4 and 6, and each one of them is 50%, so we get 5. And if we do the same thing, we should get 2 and 1 for the tax lawyer and near partners. So now, again, the main difference in this question is we have the number of hours. We didn't have number of hours in previous questions. We just assumed that they do the same hours every day, each resource pool. Now, each resource pool in this case has different hours. So when we calculate the effective capacity, we're going to take the number of professionals, which is 4. So let's start with the paralegals. So that we're starting with the paralegals, and it's 4. And here, and then we multiply it by 6. This is new. We multiply by 6 because each resource pool is working different hours. And then we divide it by TI, and this is TI, and we get 4.8. So we got 4.8 for paralegal, And if we do the same procedure, same exactly, so dividing the C and the TI, we should get 12 and 8 for tax lawyers and senior partners. Now, remember, the bottleneck of the process is the smallest capacity, and the smallest capacity in this case is the paralegal. So that will basically dictate the whole process, and hence the whole process, the capacity of the whole process is going to be 4.8 contracts per day. So part B of the question says, can the company process all 50 cases in August? We know in the question that there's 20 days per month for this law firm. So we take these 150 case and we divide it by 120 to get how many contracts per day, because all our numbers we've calculated in the previous slide were per day. So 7.5 is much higher than the effective capacity, which we've calculated to be 4.8 in the previous slide. So the capacity isn't sufficient. So the capacity is not sufficient to process all 150 cases. So let's do part B of the question. So we know that there is 20 days per month. That's given in the question. So the question is asking us, can the company process all 150 cases in August? So let's see how many cases do they have to do per day. So we take the 150 divided by the 20 days per month, and we get 7.5 contracts needed to be done per day. So 7.5 obviously is much higher than our effective capacity. This is our effective capacity, which we've got in the previous slide. So it's much higher, so the capacity isn't sufficient. So we can't process 150 cases. We cannot process all these cases. So now the question asks us if the firm wants to do all 150 available cases in August, how many professionals of each type does it need? So we know the unit load. We've already calculated this for each resource pool. And the hours required is just that number, 105, multiplied by how many cases there are. So we get 750 here, get 300, and 1 times 150, we get 150. So this is the hours required to meet the demand of 150 cases. Now the hours available, this number is basically, remember we had only each resource unit could work 6 hours per day, and we know that there's 20 hours per month, so we get that 120 number. And then this number is basically our overall, our basically hours required, 750 divided by the hours available, which is 120, which tells us how many workers do we need, how many resource units we need. So when we go 750 divided by 120, we should get 6.25. Of course, you have to round this up because you can't hire 6.25 people, so 7 people. So you need 7 people in total. So you need 7 people in total to meet the target of 150 cases, and we do the same for the rest of the resource pools. So that's so remember we have to round up each answer, and that's basically it for the last topic of the class. We are basically finished all the material for the final examination.